All right, legends, this is Mr. Mays coming to you through the virtual space. Happy snow day. Be aware that this is a, synchronous lesson. Just keep in mind that alongside what we're talking about today, I'm going to give you a couple of extra pointers as to how you should spend today, because if this is you coming in the future to review for AP, be aware that today was a snow day, and so there are a couple of extra directions for facilitative reasons. But let that not distract us from the main goal of today, which is, of course, 7.3, the final day of actual notes for this unit on hypothesis testing, aka significance testing. And 7.3 is, of course, our focus on significance testing for means. Yes, indeed, my heroes. Significance, I should say, testing for means. So, we will bear in mind, of course, that everything we talk about today is in many ways a reiteration of what we did with proportions, but I will walk you through every step, so worry you not in your sweet little hearts. First thing first, if you go ahead and pull up your 7.3 slideshow presentation, it is posted up on Canvas. It will do you well. Be aware, of course, that the first couple of slides are the answers to the 7.2 homework. I also threw in fixed edited responses to number 53 for those, because I believe number 53 was written incorrectly, or at least it was written for the wrong problem, and I went ahead and edited that and then threw it up on Canvas. So you should use that as your reference point. And I would highly recommend that you go through the 7.2 notes, and of course the videos for 7.1 and 7.2 as well, okay? So because today's an asynchronous day, alongside these 7.3 notes, take the time to go through 7.1 and 7.2 videos to make sure you're really acquainted and ready. Next class will be a review day, at which point we will then take the test. So for my Red Day legends who are having this off day today, the situation is such that on Friday we will have our review day, and then the following Wednesday, because Monday is off for President's Day, the following Wednesday you will have your assessment. Okay, enough talk, Mr. Mays. Let's hop in, all right? I do my like New Yorker thing. All right, guys, let's hop in here. We're going to talk a little bit today about significance tests for means. Let me show you every inside out and backward methodology you're going to need for this. If you take a look at slide 9, I take a moment to interpret the p-value for you. That is as follows. This is true no matter if we're doing means or proportions. The p-value is assuming, and you may have to say this in a problem or an answer, if I ever tell you to interpret the p-value. Okay, this would be like a key set of words to look out for, both on the AP test and on my assessments, right? You would say, assuming the null hypothesis, and then you would state what that null hypothesis is, right? So give me context, is true. The probability of observing our sample statistic, be it a sample mean, which is an X bar, or a p-hat. Oh no, don't do that. Or more extreme. And I say more extreme because it could be that we are looking at a one-tailed test on the low end, in which case more extreme would be or smaller. But we could be also looking at the upper end, where more extreme would just mean greater. We could also be doing a two-tailed test where more extreme is simply in both directions, right? So that or more extreme is, and then you give the p-value. That is what a p-value is. Okay, we're back in. We've dipped our feet. Slide 10 goes over type 1 errors and type 2 errors. I would review those again, but again, I go over those in the 7.2 video notes, and I talk about them at length, or at least I did when I was going over the homework with you last class. Okay? So, know your type 1s, know your type 2s, know what power is, and know that a type 2 error, the odds of a type 2 error happening plus the odds of power come together to make one whole, right? And then know that a type 1 error's percentage is directly equal to your alpha. Slide 11, we make this very important correlation, this sort of background. And all of this is just to get us geared up. But be aware that a 95% confidence interval gives us the same info as a two-tailed significance test right, at an alpha of 0.05, right, aka 5%. And let me write 5%, actually. That's how I want to write it. So what we're saying here is that a confidence interval at 95% confident will make the same argument. It makes the same claim. It gives essentially the same ideas as a two-tailed significance test with an alpha of 5%. What does that mean? Well, that means, mind you, if you are rejecting the null in this significance test, right, it is because the value you got in your sample data didn't fall in your interval. So if it fell below the 5% marker, that means it did so on both sides if it's a two-tailed test, and therefore it fell outside of your 95% confidence interval. So that's just something I want you to keep in mind. That will come back, not to haunt us, although maybe haunt is the word, because legends, what are we returning to? He's a phantom. I'm going to get copywritten for this one, for throwing in the Danny Phantom theme song. This is going to come back to bite me. Which reminds me, don't you sometimes like to listen to great ads all the time? You should look into Raycon earbuds. I'm kidding. Okay. So if we turn to slide 12, we are back to phantoms. Phantoms will follow the same rules it always has. Let's walk through it, shall we? I'm going to go through with my favorite color, orange. Let's roll with some orange today, heroes. All right, let's start where we need to start. P, state the parameter. What's that going to look like for means? Of course, it will look like the true mean. And then you'll give context. And that's all. That's all you'll do. You'll say the true mean height in the classroom, right? The true mean weight of U.S. adults, whatever that is, okay? And that's how you'll open. You'll open with, that is my parameter. Moving on to slide 14, we roll in with our hypotheses. Again, this will follow the same process that it followed with proportions. Your null hypothesis will be stated. How will you state it? You'll do a colon after the H with the O in the subscript, the ho, and you'll say that the mean is equal to some null mean that you are offered, right? It's always equal to when it's the null hypothesis. On the other hand, your alpha will be set to either be less than the null proportion, or the null mean, I should say, greater than the null mean, right? Or simply not equal to the null mean. And you will mark in your own minds the fact, let's do blue for this, that these two up here signify one-tailed tests, whereas this guy over here is a two-tailed. We'll highlight this in green. Okay. So we've got our situation, our null and our alternate hypotheses, all of these circulating around means. We're then going to go to, honestly, my favorite part. I think you probably can guess this is my favorite part. These are our assumptions. We've got three options here. 1, 2, and of course, 3. First one, is it random? Hey, good news. It'll be stated as random at some point in the problem. Okay? Same as always. Is it independent? Same rules as we have for proportions. I need for the population total to be greater than 10 times the sample size. Okay? So you'll do 10 times your sample size, and you will say we can presume that the total population is greater than that value. Remember that that's independence. On the last hand, we need it to be approximately normal. Otherwise, we cannot make any discernible notations. Okay? With that in mind, there are two main ways that we check for it to be approximately normal, and that is that n is greater than or equal to 30, aka the central limit theorem. We know this. We've said it many times. It's all the same stuff that we did with confidence intervals. But of course, the other option is that we have a normal graph. of sample data. Right? No skew, no outliers. And that will ensure for us that we indeed have a normally distributed situation, and we can start doing our work. So let's presume that, just as always, we've gotten a checkaroo, and a checkaroo, and we are set to roll. Back to orange. We've hit our assumptions. Now we're going to name the test. We're going to name it. And what are we going to name it? Well, as you are aware, we are often only given the sample standard deviation. Oh, I shouldn't circle that because I've been circling the letters. Okay, sample standard deviation. So because of that, we are doing a t-test, not a z-score. We know a t-distribution when we see one. We've gone through the notes on this. So what is the name? The name is, of course, Long John Silver. Now, one sample t-test for means. This is slide 16, and you're just going to name it. That's what you're going to name it, and you're going to be happy you named it that. Everybody else is naming it that too, but that's because they're getting full points on the AP exam. Don't worry about originality here. Okay, that's not true. Actually, do worry about originality, but make sure it's entirely correct. We move on to T. What is T? T is the test statistic. Oh, now bear in mind, just as with proportions, you can calculate the test statistic and the next step of obtaining the p-value all in one if you follow the calculator functions I will show you in a moment. But first, let me just show you how we set the test statistic. We are going to be looking for a t-test statistic that is equal to x bar. Mind you, I just want you to keep in mind, this is the same equation as we had for proportions. It's all going to roll the same way, except it's going to be the sample mean, which is x bar, minus the null mean, right? So we find the difference between those two, and then we divide in the standard deviation for our sampling distribution, which for a t-distribution looks like this, right? It's going to be the standard deviation for the sample over the square root of n. What do? You take that, which, mind you, this down here is just the standard error. You calculate that first, then you divide it into the difference between x bar and the null mean. Moving on, you will then obtain the p-value. And I have the sketches for you here on slide 18 for a situation where your mean is argued to be greater than the null, right? That'll be the one where we have the sketch and we are in fact looking on the t-distribution for values that are above. So what we're going to do is we're going to do t-CDF, not norm CDF, because we're doing t-distribution. So this is our first time with t-CDF. T-CDF is so wonderfully easy. You will set your lower bound. If you are in a situation where our mean is argued to be greater than the null mean, then in that situation, you will make the lower bound the t-value, the t-critical statistic, the test statistic as we call it. And then you will make the upper bound 100,000. And then you'll just put the degrees of freedom, right? Which is n minus 1, if you remember. Okay, so sample size minus 1. You'll do the exact same thing, except you will do it in opposing order. If you do a situation where the p-value is such that the mean is supposedly less than the null mean, what will you do there? You'll do the same thing with t-CDF. And this is all noted on slide 18, these different variations. But in this situation where you have it be less than, you will have your lower bound be negative 100,000. And your upper bound will be your t statistic. And then, of course, you'll throw your degrees of freedom in. If you end up in the last situation, where we're simply saying that the true mean is not at all equal to the null mean, then you will just run your t-CDF situation. I would do the upper bound one, but it's entirely up to you. It'll depend on the scenario. It actually doesn't really matter. You'll do one of them, and then you will multiply it by 2. So let's say you do lower bound t statistic, upper bound 100,000. And then you will take that value and you will multiply it times 2 to get both tails. And that's it. We move on to slide 19. And on slide 19, I give you the secret sauce. Let's say you're like, Mr. Mays, that was all well and good, but I just want to do both T and O on the calculator. Calc style, as it were. What do? The directions are up there, right? You're going to go to stat. You're going to hit test. You're going to do t-test, because it's a t-test. T-test is number 2. Then you got to scroll over to stats. Don't put in raw data. Raw data will scare us all. Then what do? You put in your null mean. You throw in your x-bar, which is your sample mean. You throw in your standard deviation for the sample. You throw in your sample size, not your degrees of freedom, your sample size. And then you will set your mean to either be not equal to, less than, or greater than. Excuse me, and pardon me. And once you do all of that, as your calculator input, you can roll accordingly. So if you were going to write this on a test, you would simply write at the top, t-test, and then you would write down the following information that you input, whichever one you did. You would highlight the one that you did. Let's say that I did this guy. I did it does not equal a two-tailed, and then you would go on. All right, and then with that all concluded, we have one final push, and that's our m/s, which is where we make our conclusion and state it in context. What you do for that is for the m part, technically you state that your p-value is either less than the alpha, or it is greater than the alpha. And all the descriptions are written on slide 20. If the p-value, of course, is less than the alpha, we successfully reject the null, state that in context, right? And therefore have convincing evidence for the alternate. The only key here is that the stating it in context means you have to state what the null and what the alternate are in context. So we reject the null height, or the null hypothesis that the mean height for all students is 5'9", because there is convincing evidence that the mean height for all students is greater than 5'9", if that indeed was our argument. If, however, the p-value is greater than the alpha, we fail to reject the null, and we do not have convincing evidence for the alternate. Okay? And all of this, of course, is on slide 20 once again. So be aware of all of that. I will then have you note that on slide 21, we have a problem. It's about a typical US runner. I want you to take a moment. I want you to pause the video, and I want you to solve this example t-test for mean that is on slide 21. You will note that on slide 22, I have literally posted the answer to this particular problem. But go ahead and, without going on to slide 22, staying on slide 21, go ahead and pause this video and answer the problem. All right, you should unpause the video. Hopefully that was long enough. For me, it was but a few seconds, but for you, it must have been an eternity. But hopefully you went through and you ran through your phantom steps that we just went through, and you gave the context, right, for the parameter. You went in and you rolled and gave me a null and an alternate hypothesis. You then stated that your 3 assumptions must be true. You rolled through and named your t-test. You went and calculated your t-test statistic and obtained a p-value. And then you closed it all out with a convincing end to your story, making a conclusion and stating it in context. And you then cross-checked it on slide 22, where we state the calculations in a very textbook way. You'll know what the correct answer is. That is how we do what we do. You'll notice that on slide 23 and slide 24, you get to test the degree to which you are comfortable with what a type 1 and what a type 2 error is. And then on slide, or that was on slide 24, I should say specifically. And then on slide 23, you will look at what whether you would expect a 95% confidence interval to contain a particular value. That goes back to a hint I gave you earlier on in this very set of problems. Very start of this video. So I want you to scroll back and look at that. This notion that a 95% confidence interval mirrors a 5% significance test that is two-tailed. Excuse me. So you should try your best to answer those two problems. Solutions will be provided next class. Moving on to slide 25. I'm going to warn you, and by warn you, I mean just offer you, frankly, a bunch of encouragement. You've been heroic so far. You've already gone and done your own t-test statistic and shown whether there is or is not evidence to reject the null hypothesis for a mean. What we will add to that sauce, so to speak, now, let's pick a different color. What are we feeling, heroes? I'm thinking this like really cute turquoise blue. Yeah. Let's be a little wild out here. We are now going to do paired t-test. Now, fear not, my heroes, for I have haunted you well and enough with phantoms. We know phantoms inside out and backwards, and I'm going to go through it one more time with you. On slide 25, I state to you that studies sometimes involve two observations. The example I give you in the notes is UCLA, the university's textbook prices, versus the Amazon textbook prices. And what we're doing here is we are comparing two means, right? A mean textbook price for UCLA and a mean textbook price for Amazon, okay? You are going to note that if we ever do a paired t-test, which is what this is, it is paired because we have a paired set of values, two means. The calculations are all the same, and I have to give you all of these values. So worry you not, and let me just walk you through it. Even it says on slide 26, the work is almost exactly the same as with one sample data, just a few small differences. Let's go through and note them. Step one, go to slide 28 with me. We're using this example of UCLA prices versus Amazon prices. What do? We define the parameter, right? The parameter in this case will be the mean difference, right? So the true mean difference. And then I will give context. So in this situation, it would be the true mean difference between UCLA book prices and Amazon book prices. Easy, right? We move on to slide 29, I should say. We're rolling with the ancient phantoms. What do we do? The same deal. Okay, give your null, give your alternate. You will note, slight difference here, the null is almost always that the mean difference is 0. Almost always. Now, sometimes the problem will try to be sneaky with you, but you aren't going to fall for those sneaky tricks. You're not going to be played by those traps, right? But sometimes it'll try to be sneaky, and it'll say, oh, the mean difference is normally, or is agreed to be, $5 between the two. However, the alternate is that value is different, right? Or whatever it is. But normally it'll be that the mean difference is 0 and that the alternate is either less than 0 or greater than 0. Or, of course, once again, simply not equal to 0. I'm not going to bore you. These are all the same rules as we had with a regular t-test and even with probabilities, right? It's all the same. We check our assumptions. Assumptions are one fewer this time. Random, it must be stated. Okay. Approximately normal we still need, right? And the rules hold the same. The song stays the same. We need either the central limit theorem, so n is greater than or equal to 30, right? Or, right, graph of sample data. Is approximately normal. So not perfectly normal, but I can't have a skew, and I can't have any outliers. You know what we don't need? And you don't need to say anything about it. You can just stop there. It is not independent. Why is it not independent? Well, you already know. We're taking UCLA prices, and we're comparing them directly with Amazon prices. And in any paired t-test, you are directly comparing two entities, one to the other. That is necessarily dependent. Now, you don't have to say they're dependent. We know they're dependent. But don't say that they are independent. No independence here. Necessitous dependence. Sorry, I'm really taking this whole phantom thing to heart. Halloween's past, man. All right, Slide 31, we're going to name the test. The name is slightly different this time, just slightly. It's called a paired t-test for mean difference. And that should make sense. Why are we doing a t-test? Because we only have the standard deviation for the sample. We'll call it a paired t-test for mean difference. Then we will calculate the test statistic. Again, you can use the calculator function, the one I already taught you. If you want to skip this step, right? Roll through on stats, go through, plug everything in. But this is only if they need you to just plug and chug. In case they need you to calculate just the test statistic, what will you do? It's the same equation, heroes. It's x bar, but this time it'll be the x bar for difference, minus the null proportion for difference over the standard deviation for the differences over, once again, the square root of n. And n represents the number of pairs. Don't let that confuse you. When I say number of pairs, it's the same as number n, right? It's just how many groupings of UCLA textbooks compared to Amazon textbooks we have. Then you're going to obtain the p-value, all the same deal. Use TCDF, not norm CDF, right? Do your lower, do your upper. The rules will be the same. The sketches are provided on slide 33. Everything is the same. If you're saying it's truly greater than 0, you're going to make your lower bound the t-test statistic and your upper bound 100,000. If you're saying that the true paired mean is less, you're going to make your upper the t-test statistic and your lower negative 100,000. Then we ended up, we're on the final slide. MS, well, not the final slide, but the final new concept when it comes to paired observations, right? We are going to make our conclusion. It's the exact same as it would be for a single test, okay? I want you to go ahead and scroll over to slide 36 with me. You will notice that though this slide looks scary, at the very bottom, I have 3 things listed. N difference. What is that? Number of differences. 73. That's your N. Okay? X bar. Your X bar here is 12.76. Okay? That's your X bar for difference. And then your standard deviation of the differences for the sample is 14.26. Okay? You'll notice I have to give you these values. You don't calculate these values. You will then use this and solve it. Here's what I want you to do. I want you, using slides 35 and 36, do not go to 37 yet. I want you to use slides 35 and 36. Do it right now. I want you to pause this video and use slides 35 and 36 to solve for a paired t-test using phantoms. Do that right now and pause the video. All right, I hope you paused that video. I hope it took you as long as you could possibly need to fully understand it. And now you are with me again. I want you now to scroll over to slide 37. I want you to see how I set up the null and the alternate hypotheses for this problem. I want you to note how I solved for the test statistic and then for the t-value, okay? Well, actually, that is the test statistic. For the standard error, I should say, and the t-value. And then I want you to know what the p-value would be for that particular scenario. Make sure it hits as it should. And lo and behold, legends, you're done. You are done for today. I want you to drink up the snow outside if there is snow outside. If there is not snow outside right now, because you're watching this video later, I want you to drink in the fact that you have fully mastered and learned all the components that you need to understand how to do both a paired t-test and just a one sample t-test for means. Okay? You know every step. That is 7.3 completed. Again, the next time I see you, you will have reviewed 7.3's video notes that we just went through. You will have reviewed 7.2 and you will have reviewed 7.1. And you will be ready for our big old review day, followed by your assessment on Unit 7, Significance Testing. I am so proud of you. I am so honored to be your teacher. Drink up the brilliance of what is a significance test and know this stuff inside out and backwards. Review your type 1 errors, review your type 2 errors. Remember, type 1 errors are your alt people, type 2 errors are your old people. With all of that locked in, I'm proud of you. I'm thankful to be your teacher. I want you to enjoy today. This is Mr. Mays signing